In this video, we discuss learning outcome number 1 from lesson 5.2, which is all about binomial probability distributions. First, we're going to describe what it means for a procedure to yield a binomial probability distribution. And then we'll look at a procedure and determine whether it meets the necessary requirements. So here are the 4 requirements that are necessary for a procedure to yield a binomial probability distribution. First, the procedure itself has to have a fixed number of trials. A trial is just a particular observation. If you are thinking of flipping a coin and you're flipping a coin a number of times, let's say you're flipping a coin 100 times. Each flip of that coin could be considered one trial. In that case, if you flip the coin 100 times, you'd have 100 trials. So it's basically that our procedure involves doing something over and over again, but we're doing it over and over again a fixed number of times. And that thing that we're doing over and over again, that's when we look at that one unit, that's called a trial. Now, the trials themselves have to be independent. And remember what independent means. That means the outcome of any individual trial does not affect the probabilities of the other trials. So let's say you're talking about getting heads or tails. You flip the coin and you get heads. The next time you flip the coin, that second time you flip the coin is not at all affected by what happened during that first trial. During the first trial, you could get heads or tails. During the second trial, it doesn't matter. You can still get heads or tails. So the probability of success remains 1/2 in the second trial. And it's not at all affected by what happened in the first trial. That's what we mean when we say the trials must be independent. So all of the trials in our procedure have to be independent from each other. The third requirement is that each trial must have all outcomes classified into exactly 2 categories. That's why we call this a binomial probability distribution, because there are 2 categories. Typically, we call those categories success and failure. We say if this happens, we're going to count that as success. If anything else happens, we're going to count that as failure. You don't have multiple outcomes, or if you do have multiple outcomes, you've classified them into these 2 groups. You're thinking of the outcomes as being either success or failure. And then finally, our 4th requirement is that the probability of success in one trial remains exactly the same from trial to trial. So if the probability of success increases as you go from one trial to the next, well, then that's not going to represent a binomial probability distribution. So we've got some notation. There are a lot of variables or letters that you're going to see in our formulas. Kind of looks like alphabet soup sometimes. I don't want you to be confused by all of those letters. They each represent something, and it's usually pretty easy to understand if you can remember what all of these letters represent. So the lowercase n, that represents the fixed number of trials. So if we are flipping a coin, the number of times we flip that coin, let's say we flip the coin 24 times, then the number of trials would be n equals 24. Now, x is a particular number of successes out of those n trials. So if you flip the coin 24 times and you decided that success was going to represent the number of times that you get heads, well, you could get 0 heads, 1 head, 2 heads, 3 heads, all the way up to 24 heads out of those 24 flips of a coin. So the value of x can be any whole number between 0 and that number of trials inclusive, because it's possible that none of the trials are successful, and it's possible that all of the trials are successful. And then there's also the possibility of having any number of successes in between. Now, lowercase p will represent the probability of success in one trial. I've got a little asterisk there because we're going to come back to that word success and what we mean by success. If p is the probability of success in a single trial, q, which is defined to be 1 minus p, that's the probability of failure in one trial. And this probability of x at the bottom here is the probability of getting exactly x successes in n trials. Now, this word success that we keep using is arbitrary. Anything can be defined as success. Success doesn't necessarily have to represent something positive. So if you're talking about a birth and you're talking about whether you have a girl born or a boy born after that birth, you've got one of those two possible outcomes. You could define having a boy as success, or you could define having a girl as success. And when we say that having a boy is success or having a girl is success, we're not saying anything negative about one gender group or another. We're just saying, like, this is the one that we're calling success, and this is the one that we're calling failure for the purposes of our statistical analysis. Success doesn't have to be positive. Also, you could talk about whether you got an answer correct on an exam, or whether you got a question correct on an exam, or whether you got a question incorrect on an exam. So you might think that we should say that success is getting it right and failure is getting it wrong. But when we are using the word success in statistics class, it doesn't matter. It could go the other way. You could say that success is getting it wrong and failure is getting it right. It's really up to you. So either of those categories can be called success. You've got two categories, one's success and the other one's not. Now, the probability that's associated with success needs to be identified as the letter P. So it's really important that you understand what X represents, what you are defining to be success, and what is the probability that goes with that particular event. So you've got to be consistent. So if X is the number of correct answers on a test, P is the probability of getting that answer correct in one trial or given one particular question on that test. So just make sure that that P represents to the probability of whatever that is that's we're categorizing as success or that we're labeling as success. And you're not accidentally associating X, the number of successes, with the probability of failure. Just got to be consistent. This is just a note from me. It just says that it's helpful to state your definition of success as you're working problems. That will help you keep track of what X actually represents and then what probability should go with X. I always like to write it down. I've got an example here. This is really cute. This is a clinical trial of a gender selection method called Y-sort. The Y-sort method of gender selection was designed to increase the likelihood that a baby will be a boy. The problem statement says when 291 couples use the Y-sort method and they give birth to 291 babies, the genders of the babies are recorded. The question is, does this procedure result in a binomial probability distribution? And if it does, identify the values of N, X, P, and Q. Okay, so if we want to decide whether the procedure meets the requirements of a binomial distribution, we have to look at all four requirements. First, we have to think about that number of trials. We have to ask ourselves, is there a fixed number of trials here? Well, we're dealing with 291 births that result in 291 babies. So yes, there are 291 trials, and 291 is a fixed number. The next question is, are those trials independent from each other? Does the outcome of any birth affect the probability of the outcomes of any of the other births? Or in other words, if someone in that group has a boy or a girl, does that at all affect the probability whether the next couple has a boy or a girl? It doesn't. So the trials are independent, which is good. So 2 of the 4 binomial probability distribution requirements are met. Now, the last 2 requirements are that all outcomes fit into one of 2 categories. And that's absolutely true for this, because if you're looking at a birth, you either get a male baby or a female baby. And then lastly, we need to check and make sure that all trials have the same probability of success. If we choose to define a male baby as success because these folks are trying to increase the probability of having a male baby, then the probability of success is going to be 1/2 in all trials. Since it's exactly the same probability in every trial, that means that fourth requirement for binomial probability distributions is met. So it is a procedure that yields a binomial probability distribution. Okay, with that in mind, we need to define n, x, p, and q. Well, n is the number of trials. So that's 291 trials because you have 291 births. Now, if we're trying to increase the likelihood that a baby will be a boy, and you've got two options, either the baby is a boy or the baby is a girl, then x might be defined to be the number of baby boys. So we might say that having a baby boy is a success. The probability of having a baby boy is 1 in 2, or 1/2, so that's our p-value. And lowercase q, that's the probability of having a girl rather than a boy. This is the probability of failure in one trial. So if p is the probability of success, and that's 0.5, q is the probability of failure. So that's 1 minus p. 1 minus 0.5 happens to be 0.5 as well. So that's the probability of having a girl. Now, if I wanted to find the probability of having 156 boys out of those 291 trials, we would have to use binomial probability distribution formulas. Those are binomial probability formulas that we'll talk about in the next video. Oh, not in the next video, sorry, in the video after that.